Hello everyone, and thank you for attending our presentation today. And we will be discussing about quantile mapping climate model simulations. I'm Dr. Chandra Rajulapati. I'm a postdoctoral research fellow with Dr. Papalexiou at the Center for Hydrology, USASC. And yeah, I have previously worked with Dr. Samantha as well, and Professor John Bomrai. As Laila mentioned, that this is not a very formal session. So if you have any questions, or if you want me to stop in between, and then if you have a question, just please raise your hand, and then I'm happy to answer your question. So yeah, I would like to start my presentation with a land acknowledgement that I'm currently in Saskatoon, and we acknowledge that we are on the Treaty 6 territory and the homeland of the Métis. We pay our respect to the First Nations and the Métis ancestors of this place and reaffirm our relationship with one another. So here is the outline of my presentation. So I'll be giving a brief introduction about the climate change impacts globally, as well as what is happening in Canada with respect to the temperature. And I'll be discussing about the latest phase of CMIP, which is the Climate Model Intercomparison Project, which is CMIP 6 currently is the latest phase. And I'll be discussing on how to download the data from the ESGF portal. There are several ways. I'll also explain them how one can get the data, CMIP 6 data. And I'll be, before going to the quantile mapping or the bias correction, which is a form of, quantile mapping is a form of bias correction. I'll be showing the biases in the temperature and precipitation, which in the CMIP 6 at global scales, which we have performed for temperature and precipitation before. And then I'll be discussing about the different methods of quantile mapping and what are the differences between these. And then we have also introduced a semi-parametric quantile mapping, and we'll be discussing about how to do the SPQM as well. And I use R, so I show some of the R packages which are readily available for doing the quantile mapping. You don't have to develop your own method, but there are readily available good packages, I would say. And yeah, so I'll be also discussing about the criticism about the bias correction in general, and also the quantile mapping, and then finally conclude the presentation. So coming to the introduction, so we have been noting that the global temperature has been increasing at a very higher rate compared to the previous decades. So if you see the temperature from 1970 onwards, after about 1960, the rise in the temperature, this is the global temperature anomaly rate, we see that it has been increasing at 0.2 degrees centigrade per decade. And the rate of increase is more concerning than the temperature has been increasing from ice age to now, but the rate at which it is increasing is concern for us now. So if we look at the Canada's temperature, it is increasing almost double the global rate. So the global rate is at 0.2 degrees centigrade, but the Canada state is almost 0.43 degrees centigrade per decade now. So this increase in the temperature or the impacts of climate change have there are several impacts of this climate change. For example, first thing is the changing extremes. So the floods, droughts, wildfires, they have been changing drastically over the globe, and we have also been noted the increase in sea levels, and the coastal populations are already having the severe effects of the increasing sea levels, and there are also several effects on the ecology. So if you look at the temperature changes in historical temperature changes in Canada, there have been a huge increase from 1979 onwards. So if you look at the northern part of Canada, almost 5 degrees centigrade has been reduced in just about 40 years, and even the gray part has been shifting upwards. In 1979 it used to be here, and it has been shifting towards the north. And even the southern parts of Canada has been increasing. The temperature has been increasing at a much faster rate compared to the other regions of the globe. So we definitely have noted the historical changes or historical increases in temperature at least, and then they have certainly the effects on the precipitation and other variables as well. And it is important to understand such changes and historically as well as how they are going to be in the future. So one tool we have right now to understand the projected changes are the climate models. So the climate models are basically, they divide the Earth into different grids and then they try to solve the, energy mass momentum equations at each grid from one grid to other grid. So we have this CMIP, which is a part of a, World Climate Research Program. And there are several experiments conducted to better understand the present, past, and the future climate and its variability as well as its variability in a multi-modal framework. So we are currently with the 6th phase, CMIP 6, and yeah, these are definitely useful for risk assessment, especially when we consider future projections. So I'll start with how do we download the CMIP data. So here we have, I'm showing the first one is this Earth System Grid Federation, or ESGF in short form. So there are four, okay, let me try to get this up. So there are four, ESGF portals where today I'm showing about with the LLNL, which is the Lawrence Livermore National Laboratory in USA, but there are also other ESGF nodes available at IPSL, CEDA, and DKRC. So this is how. So if I just go to the Google and try to, for say CMIP 6 data download, the first one appears in this ESGF web page. So it could be from LLNL or it could be from IPSL or anything. But if you open this, there are two interfaces which are which you can download the data. So one is the CMIP 6 search interface, and there is the new one. They have started this recently with this MetaGrid, where you can select the models depending on your requirement, on where you want, which variable you want to download, or which okay, yeah. So you can select in general the resolution, the classification, additional properties, file name, etc. But which I use and which is automatable is this web page, the first one here, the CMIP 6 search interface. If you click on this, that you will end up in opening up this page. So here I can select a modeling group or a model, CMIP 6 model, and which experiment ID. Here I have selected historical, so it could be, for the future scenario MIP you can select, which would be SSP 58.5 scenario if you want to know how the temperature or how your variable is going to change in the future period. And then, you can select the different frequency. Here I have selected precipitation and then daily. So when you hit the search button, so all the files are displayed here. So if you are registered with this, and it is a very easy registration, you just have to give your institute ID, and also they will give you the immediate access here. So if you can log in, so you can just display, you can add them all to your data card. So you can just add all displayed results to your data card, and then if you go to your data card and you select the all data sets, and then you just create this wget script. So this is as easy as it. So you just, download this data script, and then you will have the wget script, and you can, run it on Graham, or you can run it on your PC, or it is as easy as that. So this basically contains the links from which the data has been downloaded. Or yeah, these are the links from where it downloads. So this is the link basically from where this particular file has been downloaded. So this is very easy, and it is easily automatable also. You don't have to do it manually. So you select the models and then just add to your data card and then generate the script. So
Chandra, I'll just interject there. If you go a little bit slower, it might help. There is still that audio feedback issue that we tried to fix, and I think it didn't make that big of a difference. So if you maybe talk at a slower pace, it might help with that.
Okay,
It just gets muffled. Yeah, when you speak faster, the volume gets a little bit more muffled. So I hope that that'll help. Thank you so much.
Oh, no worries. Thanks for letting me know. I'll try to speak slow. Yeah. So yeah. So this is the easiest way, and I also follow this. So I consider it easy and as well as automatable. For you don't have to. There is not a lot of manual work involved here. But there are also other places from which you can download the CMIP data, which one such is the Climate Data Center. They also have an API, I guess, so this also should be easy. But I haven't used this as much as I use the ESGF portal, and this is by the Copernicus. There is also another source which you can work directly from the cloud. So all the climate data or CMIP6 data has been, uploaded on the Google and Amazon cloud, and there are scripts available to download from the gallery. So this is one such script where you can get the Python script, and then you can you pull the data from the cloud, and then process it, and then use and then you don't have to download the data fully onto your machine. So which also saves a lot of memory and time as well. But the only the drawback here, which when I started using this, there are two issues which I have faced. One thing is the ESGF is always updated. Sometimes there will be a delay in updating this cloud, so you have to be careful whether to make sure that the data is updated on the cloud. And the second issue is, I found that working with this is a little bit slower compared to downloading data from the ESGF and then, downloading it and then processing the file. It could be because maybe I'm not good at Python, so maybe if anyone is very good at Python, you can, explore how, if you can, maximize the speed of the code here. And one more disadvantage of working with the cloud is that you can, if you are using just for one time, it is the best option. You don't have to download the data. But if you are trying to use for several applications, then always pulling the data from the cloud and then working with it and getting the output, it takes some time. But if you are just working for one time, this is the best option, I would say. So the if you look at the name of the CMIP6 files, you don't have to go inside the CMIP NC files and then see what is in there. So if you look at the name, it has a very clear explanation of what it is going to contain. For example, this is one file name which I have got it from the ESGF webpage, for which I have downloaded the duplicate script. So if you see, obviously this is a variable name which I have selected as maximum temperature, and this is the temporal resolution, and I have selected because I wanted a daily scale. So this is the model name, or you can also get the modeling group from the ESGF webpage directly. And this is the experiment ID. I mean, previously I've shown for the historical, but I have selected here SSP 58.5 scenario, or this that's the experiment ID here. And this particular number gives, this is called as a variant label. This is used, I'll get back to this variant label when I talk about the internal variability. But basically these are the indices, 4 indices R, I, P, F. They basically represent the realization, initialization, physics, and forcing. So these are the 4 indices that describe the position of this individual member within the ensemble for of this experiment conducted by this CAN-ESM5. So this is the 13th realization, first initialization, second physics, and first forcing method. So if you are interested in what is this initialization, what physics they have used, and what forcing, so you should go deep into this CAN-ESM5 documentation, and then you can understand what they have been done. And this next is this one. It represents a grid label. The grid label, which means that if you see a GN, the output, whatever they have reported, is at the native grid. So whatever the climate model have run, that same grid has been given as an output. But if you have seen a GR here instead of GN, if you have seen GR, which means the output is not reported at the native scale, native resolution. but it has been regridded to a different primary grid of their choice. That the choice is made by the modeling groups again. So it could be GR1, GR2, and so on. So when you see GM here, which means the global mean output is reported, and it is not, you don't see a time series, just you will have the global mean. So this is not definitely a gridded data here. And if you see a Z in between here, so GZN, so which means it is a zonal mean output. And obviously this is the time period. So because this is daily, you see this 01 here, but if you see MON, which is month, you will just see the month and the year here. But this is daily, so you see the day, month, and the year here. And from this is from 2015 to 2100, which this is the projections, because I have selected the experiment ID of SSP5 8.5. So I'll get back to this experiment ID. What here we have considered in our current analysis, we are considering only historical and the tier 1 scenario MIPs. The tier 1 scenario MIPs are these four: SSP5 8.5, 3.7, 2 4.5, and 1 2.6. These are the four scenarios we have been using currently, and they basically represent the forcing by the end of 2100. If I consider an SSP3 7.0, that is the 7.0 is the forcing by the end of 2100. So this is the 2100, and we are currently at this 2020 here. So these are the different roadmaps on how the forcings have been assumed for the predictions. So yeah, once we know that we have some CMIP data, we should first understand before we even use it, how much is the bias. So naturally we compare the historical simulations with the historical observations. So we have some observed data, and we also have some historical simulations. We try to see how much is the difference, or how much is the bias between the observations and the historical simulations. So here again, we have considered only the temperature and precipitation in our analysis, and we just don't look at the mean bias or the bias in the variance. We also consider the higher order statistics, which I explain in a minute. So we start with the global temperature anomaly, which we have been seeing that it has been increasing at a faster rate. So we would like to see if climate models have the same path or not. So here I am showing, about 200 plus simulations of the ensemble members pertaining to each climate model. So here the black lines represent the observations. The red line is the multimodal mean. So this is the mean of all these 200 plus simulations we have considered here. And then each modeling, each model, if you see a patch here, which means we have more than 2 ensemble members. But if it is just one, which means we have only one ensemble member for that particular model. We typically see that the multimodal mean basically traces more or less the observations here, except at this part where we see that the CMIP6 is slightly at a higher rate compared to the observations. But when we try to discretize into different time slices, we see that there is a huge difference between the observations as well as the between the observations and the simulated multimodal mean. We see in the initial time slice that there is also a difference between the observations. That is because we don't have much observations, so there could be the uncertainty in the observations as well in this time period. Yeah, the time slice 3 seems to have agreement, but this is you should understand that this is a temperature anomaly. So obviously this is a base period which we have considered to calculate temperature anomaly. So we will have a natural agreement there. So we just don't stop with discretizing the time series and for different time slices, but we also look at the autocorrelation and persistence properties. So we know that there are some models that very well are in agreement with the observations, but there are also a couple of other models which are not at all good with respect to the autocorrelation properties. So we typically look at the different properties such as autocorrelation or long-term persistence. This is important because these properties, autocorrelation and long LTP, basically gives an idea of how historically evolving time series is going to evolve in the future as well. So we have good confidence when we see these models where they are in agreement in terms of autocorrelation or the LTP properties. So we have also looked at the annual maxima temperature, where this figure shows the percentage difference in the annual maxima of CMIP6 models and other observations compared to the GPCC. However, we have also considered again, as in the case of the temperature, we have also considered different observation data sets and see if the observation if there is an uncertainty between the observations basically. And we have also looked at not just the mean percentage differences, but also the L skewness and L kurtosis and the mean and the L variation and the joint distributions as well, in terms of whether the models are able to represent well or not. And we also look at the low precipitation or the droughts, and then we have noted that the average agreement. So for example, if this is a drought, this is agreement of CMIP6 runs. There is a more or less good agreement, except in the tropics. But an interesting point to note is that if we look at the average agreement of the drought duration statistics, for example, the average of the mean duration is having the highest agreement with the symmetric models, and same as the variation and respectively other drought characteristics as well. And another important point, what we have noted is, as we have more ensemble members for a climate model, the agreement is also high with respect to when we try to see which is the best run globally. So from all this analysis, what we have noted is that the average statistics are very much better represented. And then, if we have considered many simulations, then also we could able to have a better agreement with the globally. But obviously, it is very much apparent with respect to the regional scales that there is still bias, and then this bias needs to be corrected. So one such technique which we are discussing today is the quantile mapping. What basically the quantile mapping means is that we are mapping the distribution of historical to the projected. So let us say if O is the observation, H is the historical, S is simulation, and P is the projection. So what we are trying to do is we are trying to get the distribution of the future or the historical, if you consider the historical here, of the simulations, and we are trying to map to make sure that the simulations distribution also match the observations distribution basically. So if we try to put in terms of a figure, so if we see that this is my observation and this is my simulation, we try to map these values to the observed CDF, so that the after bias correction, this pink line becomes the blue line, and which is exactly on top of the observed line. So basically the CDF of the observations and the CDF of bias corrected simulations match basically. So this is the basic quantile mapping. This is called as a basic quantile mapping. But there are several methods again and the extensions of this basic quantile mapping. The first one is the detrended quantile mapping. I'll explain in the next slide. And then the quantile delta mapping, there is also this CDFT method. There are also statistical transformations used as a quantile mapping methods. And there are again non-parametric quantile mapping methods. And then I'll finally explain the semi-parametric quantile mapping method, which we have introduced here. Obviously in the quantile mapping or the basic quantile mapping, I should say, that the biases or the time series is stationary. But however, we have already noted in the historical that there is a trend basically in the temperature time series, which I have shown before for Canada or for the global temperature anomaly. So what the detrended quantile mapping, so let us say if this is a simulated future and if you know the trend here, just remove this trend, do the bias correction and then add back that. So that is as simple as that. So this is called as a detrended quantile mapping. And these are some formulas if you are interested in noting. And the next method is the equidistant quantile mapping. So this is also called as a quantile delta mapping, or the famous QDM. But this is the same as the equidistance quantile mapping, or ED, CDFM, or there are different names for this basically. So this is a similar idea of the detrended quantile mapping, or the DQM, except that where in the DQM we have only looked at the relative changes between the mean. But in this DQM, what basically we do is that we, instead of just the trend, we try to correct the bias or the non-stationarity in the bias at all the quantiles instead of just the mean. So these are the formula, and there are several papers on this quantile delta mapping. So the next is the CDFT method. So till what are the methods till now, what we have noted is that the difference or the ratio between the historical simulation and the future simulation is calculated, and that difference is being added or multiplied to the observations, basically, in simple terms, if I have to say. But here it becomes in a different way, that we try to calculate the difference or the ratio between the observations and the historical simulations or the models, climate models, and then try to apply that same amount on the modeled future, so that we get the CDFT. So this is other way around. That's all. So this is not very different from the QDM or the other methods here. Yeah. So there are also statistical transformations where basically the a function, actually here if we try to say a function, in the previous methods we have noted that function is the CDF, but there are also could be other functions that maps a model variable or a simulation such that its new distribution equals to the distribution of the observed variable. So this was developed by this reference. And there are several parametric transformations, as well as the non-parametric transformations such as the empirical quantiles, and then there is also this popular this SSP line. So basically a line is fit to the empirical quantiles, and then try to match the lines from the observations to the model simulations. So I'll get back to the semi-parametric quantile mapping method in detail, and then explain why we need this SPQM. So as the name says that this is semi-parametric. So why this is semi-parametric is that because we use the parametric distributions for the observations and the empirical quantiles for climate model simulations. So why do we have to use these empirical quantiles for climate model simulations? Is because why can't we, fit a distribution, parametric distribution, even for the climate model simulations? Is the climate model simulations are not really good to fit a distribution. So basically, if you look at one particular grid, and then when we try to fit a skew normal distribution to the climate, so these dots are the climate model from the climate model, and this is the skew normal we try to fit. So for this kind of empirical probabilities, none of the distributions fit. So for that reason, we have to consider the empirical quantiles for the climate model simulations, but whereas we have used the parametric distributions for the observations. So why this is again, if we are trying to bias correct the historical simulations, the SPQM is same as the QDM or the CDFT. All the methods actually coincide. There is no much difference when we are trying to bias correct the historical simulations. But when we are trying to bias correct the future simulations, this is similar to the statistical transformations, which I have noted a couple of slides back. But these statistical transformations could be parametric, fully parametric, or fully non-parametric, but we are going with the semi-parametric here. And we ignore the historical simulations completely. We don't even consider them. We only consider future simulations and try to transform them using the observed CDF here. So why we have to use the parametric for observations is because when we try to use a non-parametric case, that there is there is no guarantee. Basically it's a sample of observation, so we can't basically use for extrapolation purposes, especially when we are looking at the future. Right. So when we try to fit a distribution that that better represents the entire data, including the tails or the extremes, we felt that fitting a distribution would be better than using using the empirical quantiles for the extrapolation purpose. So that's the reason we have gone with the semi-parametric SPQM quantile mapping method here. So, and one more issue which we have corrected here is that the QDM or the CDFT or the other methods have been considering only the non-stationarity in the bias. But we have also noted that the non-stationarity in the observations create a mismatch in the trend line of the mean. So we look at the scaling issues. So when we try to bias correct, so this is for a grid I'm showing here. We have bias corrected the daily precipitation and we have converted it into annual. So we have calculated the annual total from 1979 to 2100, and when we try to look at the trend line from the observations to the future, there is a mismatch in this trend line, and there is systematically all the simulations go below. They start at a different level altogether when we try to match them. So for that reason we have to do an extra correction to match even the trend line or the mean of the future simulations. So to be specific, what we do in the semi-parametric quantile mapping is we have the climate model simulations, we retrain them and then get the empirical probabilities, and we also have observations. We try to fit a distribution and then get the CDF, and then using the CDF and these empirical quantiles, we try to correct we try to match the empirical probability and the CDF of the observations, and then make sure that the empirical probabilities are mapped to the CDF of the observations, and then we try to add the trend back. And once the trend is added back from the projections, we try to also adjust the mean trend with respect to the observations. So if we look at how we are dealing with the non-stationarity, so this is the black line is observation and this is the raw simulation, the gray line. And if we try to use the SPQM without correction or the QDM, we end up having a bias corrected simulation at this level. So we do that extra correction and then try to match with the historical trend here. So this is one modification we have done with respect to the SPQM. Otherwise, without this correction, the SPQM and the QDM are more or less match seamlessly. And yeah, so I'm just presenting a couple of case studies here, which we have conducted before. One such case study is, looking at the temperature and then looking at the heat waves, how they have been changing in the historical and how they are going to change in the future. So we have considered about 18 large Canadian cities, and then we try to look at the temperature changes historically as well as the future for 4 scenarios here, starting from the lowest warming to the highest warming scenario. And we note that the obviously as the scenario say, the highest warming has the highest trends in all the cities, and the lowest has the lowest trends. And one interesting thing which we have noted here is that if we look at this line is the observed current increasing trend from 1979 to 2015, and these are the trends from 2015 to 2100. If you look at cities like Montreal, Toronto, and Ottawa, they are at already increasing at a rate which is equivalent to SSP2 4.5. In fact, Montreal is increasing at a much higher rate, which is equal to SSP5 8.5. However, cities inside the prairies like the Winnipeg or Saskatoon or Edmonton, Calgary, and all these are all increasing at a rate of SSP 1 to 0.6 here. So, and we further looked at how the heat waves have been increasing or how have been changing in the historically as well as in the future. We note that there are heat waves always, and they have been increasing historically as well and just as the warming increases, yes, the heat waves do increase. But the interesting point to note is in Victoria and Vancouver, which are the cities on the Pacific Islands, they haven't seen one. They have seen just 1 or 2 heat waves, and they increase exponentially with SSP 5 8.5 or the highest warming scenario. And obviously, with the increase in heat waves, the cold waves drastically reduce in the future for all the cities, for any of the city we have considered. So this study we have extended to the global. So we have considered about 199 cities globally, and then we didn't, note any much different results than what we have noted. But one thing to note, to consider here is the cities which are inside inside the or not far away from the water are increasing at a much higher rate for the SSP 5 8.5 scenario compared to the others. So if we look at the heat wave magnitude index, so these cities which are inside have the highest HWMI slope compared to the cities which are on the coastal regions. So that is one interesting thing to note here. And we have also looked at, of the climate models. If we use a different climate model, are we going to have a different result? So we divide our HDMI slope from different climate models and then see how much is the uncertainty from each model. And we note, there is no difference among the models. And there are a couple of models which do consider the urban land class. By which I mean they do consider the cells that are in the urban areas as an urban area, and then they consider these land interactions, the urban land processes basically. For example, the CNRM, CMCC, and all, they do consider this, and they are not, giving any different result from the other AOGCMs like AWI, and also they are more or less same. So we didn't see any difference between the models that consider urban land class and that don't consider urban land class. And naturally, with respect to, if we try to divide the time period into two time slices from 2050 to 2070 onwards, so we obviously the uncertainty increases as we go into the far future, which is an obvious conclusion. But if we are also trying to bias correct the temperature simulations for Canada. And yeah, as we see, as you note, by the time, this is for again SSP 5 8.5. So if you look at the other scenarios, other lower scenarios like lower warming scenarios like 1 2.6, the rate of increase is more or less as the historical. But as we go as the warming increases, the rate also increases again. And this is the observed from 1979 to 2014, and then this is for the near future, and this is for the far future. So you see almost the lower temperatures there. Almost entire Canada has been warming up by the end of 2100 if we consider the SSP 5 8.5. Now we look at the precipitation quantile mapping. So obviously precipitation has intermittency, and we have to treat wet and dry days separately. I'll try to fast up a little bit because we are closing almost to 11:45. So there are different approaches again to treat this intermittency, and this is one nice paper where you can go through to understand how the intermittency is being treated. But the most commonly used is again making sure that the threshold of the observed probability dry, you consider a threshold which is equal, that matches the observed probability dry. This is the most commonly used in most of the papers here. Anyway, but here what we have done is we try to match again the trend of the observed probability with respect. So if we consider a threshold that matches the observed probability dry, this is where we land up for different simulations. This is how we land up. So if we, this is again the binary classification of precipitation with respect to the year. So we have zeros and ones. So 1 is where we have the probability, the precipitation, and 0 is where we don't have the precipitation. So when we try to look at the trend of this binary classification of this probability trend, we try to match what we have left at the 2014 to start from there. So, so we have selected a threshold. So we didn't use a constant threshold there, that we have, varied the threshold basically. So we have tested this for a couple of grids, and this is for Calgary station. We have noted, and the gray line is the raw simulation, multimodal mean of the raw simulation, and this patch shows the bias corrected simulation, and this green line is the multimodal mean again. So this is for one grid, and we also try to look how the spatial variability has been, whether it has been reproduced well or not. So we have bias corrected here the historical simulations, and then we note that after bias correction, the spatial variability more or less matches. This is the observed and this is the bias corrected. So more or less matches, and even the mean precipitation and the standard deviation of all these grids, it is well represented. So the black line is the observation, and this is the patch from, we have used about 341 simulations here. So this is a patch for all 341 simulations, and the colored line shows the mean, multimodal mean of all the ensemble members here. So we have noted, good results when we have applied for the observed period as well as for the future period at a grid and at spatial scale. So we are trying to, increase, expand it to for the entire Canada right now. So coming to the R packages for quantile mapping, this MBC is developed by Alex Cannon, and this is very good for QDM, but this is a caution has to be noted here that this is only for the non-parametric case. So if you want to use it for, if you want to fit a parametric distribution, you have to use the formulas from Alex Cannon's paper, or the formulas which I have posted a couple of slides back. So there is also another, again by QMAP by Goodman Son. For this is again for statistical transformations. You can use both parametric and non-parametric transformations. And there is another package called as Climate 4R. This EQM is empirical quantile mapping. So there are some functions like empirical quantile mapping, but basically this Climate 4R is kind of GUI. Where you can even downscale to your to the point scale. And there is also another package called as bias corrector. This is the capsule, and this is basically used for bias correction, but this is not basically for quantile mapping. So you have to use caution if you want to use quantile mapping or just a bias correction. Yeah, let us see what are the disadvantages or how good is this quantile mapping. So there are, two schools of thought basically. So some say that, any bias correction or any quantile mapping, it annihilates the model capability of model's capability. But, there are also critical reviews as well in, so one such review is by around where how good is this bias correcting with specifically with respect to the precipitation and temperature and all. So there was also another good study by the same person where they note that the bias correction, so the spatial and temporal structure of the correlated time series, and that the drizzle effect of area means is overcorrected and so on. So basically, a caution is required now when we are doing the bias correction or the quantile mapping, or just before using them for your final. Based on what you want to use. Also, there are also a few studies where they say that, you don't even need a quantile mapping, you just use a linear scaling, and then, simple methods such as linear scaling or the simple bias correction, the simple bias correction, which is sufficient for hydrological analysis at maximum resolution. So I would say that the points to note before you use the quantile mapping is this doesn't any of the bias correction methods, for that matter, do not consider any autocorrelations or even the SPQM, what we have done is we try to maintain the autocorrelation structure of the simulations and then just only transform the distribution of the observations. And yeah, so basically the GCMs are spatial scale, and when we are trying to bias correct to a point scale, so obviously the autocorrelations have huge difference between the spatial scale and the point scale, which we are not correcting anyways. And another most important thing to note is that if we are whether the internal variability is being considered or not. So there are several methods again exist in the literature. Two such methods are by this IR et al. And 2021. So that these are the two methods which do consider the without disturbing the internal variability of the climate model simulations. The Quantile map, the climate model simulations again. And yeah, so finally to conclude that there are evident biases in symmetric simulations and extensive investigation, obviously not with respect to just the mean and the variation, but we need to use the higher order statistics like L-skewness or L-kurtosis, or look at the LTP, or that is the long-term persistent properties and autocorrelation structures, how they have been changing in the historically, and then how they are going to change in the future. That is also important. And yes, the quantile mapping is definitely a reliable tool for bias correction, but a caution is required depending on why you want the climate model simulations and what is the aim of your bias corrected simulations, why do you want to use them. So yeah, we are still in the development of the semi-parametric quantile mapping method, which we would also look into this, include the internal variability thing. As of now, we didn't invest much time, or we would say the internal variability is being, included. We have taken care of the internal variability, but we still have to do more, tests on this. And this also has to be extended for a multivariate quantile mapping analysis. So yeah, our work is a collaborative effort, and it's between global water features and the GEIWS and the Center for Hydrology, and obviously IMPC core modeling team, data management team, and yeah, these are the partners of IMPC. And if you have any questions, do not hesitate to contact any of us, either me or Simon. Thank you very much. And I'll stop sharing this.
Thank you so much, Chandra. Now I see why you had to move fast, and the information packed in that 1-hour presentation, it was quite a lot. I really hope it benefits a lot of the young professionals that this was especially aimed at. So thank you for that. And I am wondering, can we share some of your papers? I know that the live transcript for me did hide some of the citations. So if maybe we can distribute some of those papers, or at least the citations, to some of the audience, that might be really helpful.
Yes. So what I'll do is I'll try to put the links of ESGF portals and the Pangeo, where they can use the Python scripts, and also I'll and all my references. I'll make a list and then I'll send it to you.
Wonderful. And I'll pass it. Wonderful. Yes. And we can pass it on to all the registrants and the attendees. Saman, I see you have a question.
Sure. Thanks, Chandra. It was great. You've done a lot, and there was a lot of information for us to take in. I had a perhaps technical or philosophical question about the trending approach. So I understand the quantile mapping. My question is about the trending step. I've been thinking about that as you were presenting. So I understand that you do the quantile mapping based on the historical record, and climate model runs in the hindcast, basically to derive your mapping function. What I couldn't get my head around is that the trending phase, of course, you show the trend and there is a trend to the future. I wonder what would happen if you don't detrend that. Of course, you will end up getting a different sort of distribution. I just wonder what are the pros and cons of doing that detrending, I can see it can work. It might be an engineering approach to a very complex problem. But yeah, if you could comment on what happens if we don't and what happens when we do, and which one is really more credible at the end to the end user.
Okay, yeah, that's a very nice question, and then that is also a very a basic thing. So basically, all the quantile mapping methods, which it is QDM or DQM or any quantile mapping or any bias correction methods, they are assumed that the time series is stationary there. But as soon as a trend comes, especially for the future forcing, when we say the trend helps in a way that it is a kind of externally forced trend. It is not that implicitly that it retains inside the time series, right? So it is an external forcing there. So we try to retain that external forcing. So whatever the climate model is trying to project the trend for the future for different scenarios, we try to retain that trend by doing the detrending there. So we don't want to mess up with that external forcing there. Okay, and if what if I don't detrend? Yeah, maybe I end up in a different trend altogether, which is totally different from external forcing, or which the climate model is trying to say. If the scenario is at a highest warming scenario, the trend is going to be something different compared to the lowest warming scenario. Maybe we don't get that differences what they are trying to project with respect to the different warming scenarios.
Yeah, I guess then my question is, then you're still assuming that there is a stationarity in the form of the distribution. So you assume
Yes.
whatever distribution you've seen in the past will continue to the future. So I mean, there could be, I guess, two different camps here, one arguing against, one in favor. Yeah, I'm not sure if there has been any discussion in the literature on that, but that's a very interesting problem.
Yeah, that is definitely, there are several thoughts again, whether we continue with the same distribution or not, or whether, whether we use the same, I wouldn't say the external forcing, but basically the climate models have assumed based on their warming scenarios that the particular variable, either the temperature or precipitation, has certain type of trend or a variability. So we try to maintain that and not disturb that. Yeah, again, as you said, whether the distribution is constant or the same as the observations or not, that is definitely, there are several papers again, or in the literature discussing about this issue. Yeah, as I said, there are, two schools of thought there, I would say. One, support that, bias correction is required, and then there are others who say, no, bias correction is totally not required, or, it totally annihilates the model's capability of what it's trying to say. So there is a lot of, debate and discussion on these issues.
Yeah, for sure. Just wondering, following up what Leila said, if you could share those discussion papers as well.
Yeah, sure.
And yeah, on the two different school of thoughts, that would be helpful to the audience here.
Sure.
In addition to your own papers, yeah.
Yeah,
thanks.
Yeah, I'll do that. Thank you.
Thank you, Chandra. Thank you, Saman. We are at the last 2 minutes of our session. Are there any other questions from the audience? Comments are welcome as well. All right. I think we're good to wrap up then. But please feel free to reach out to us with questions afterward as well, and we're happy to follow up. All right, well, thank you so much, everyone. There's going to be a survey as you exit the session here. Please fill out with any feedback you have for us on how to do these sessions better. And yeah, take care, everyone.
Thank you, Leila.
Thank you, Chandra, so much for presenting. Oh, thank you so much for presenting.
Thank you.
All right. Bye, everyone.
Bye.